Now I want to take the concepts that I presented informally in the last video and formalize them in something called the limit test. So this is going to be a very important tool that you can use to determine what order of growth a function has. It's not necessarily useful if you don't know where to start, but if you have a hypothesis about what order of growth a function has, the limit test can help you seal the deal. So it can help you verify a hypothesis that you have. So this is called the limit test. Let's keep this clean. There we go, the limit test. Okay, so let's do this. And we could also call this a theorem, and number it however you like, right? So this is, but I'll refer to this as the limit test. All right, so let's let f and g be two non-negative functions. So let f and g be non-negative functions. Right? So non-negative means, essentially in the context of this class, non-negative means these things could equal running times for an algorithm. All right, so they're non-negative functions. Now let's compute the following limit. So let's compute the limit as n approaches infinity of f of n divided by g of n. Right? So this limit could evaluate to three things. So first I should say, if this limit exists, it should evaluate to three things. So this limit could be 0. It could be some non-negative constant. Right? And so I'll say here specifically c greater than 0. Or it could evaluate to infinity. Right? So what do these mean? So we've already looked at these three cases informally, but formally, what do we have? Well, suppose we have the first case, right? So suppose the limit evaluates to 0. Well, if the limit evaluates to 0, that means that g of n is growing much, much faster than f of n. It means that g of n is running away from f of n, that f of n can't possibly keep up. So the ratio will keep getting smaller and smaller and smaller because f is so much smaller than g. Right? And so what does that mean? It means f is big O of g. Right? So on the other end, what if we have infinity, right? What if this ratio evaluates to infinity? Well, that means that f is running way away from g, right? That g can't keep up with f, so that means f is big omega of g, right? And in the middle, we have that f and g are related by a positive constant. So it means that in an essential asymptotic sense, f and g are the same function, except that they're scaled by c. Right? F is c times larger than g. Right? So what does that mean? That means that f is big theta of g. Right? So if I have this situation where this constant or this limit evaluates to a constant, then this means f is big theta of g. And I'm leaving off the f of n, g of n, just to keep this compact. All right. What if I have 0? Well, I already mentioned that. If I have 0 or c, then that means that f is big O of g, right? And why does this include the constant? Why does O include the constant? Remember, O is less than or equal to, right? And so the equal to captures that constant. And then last, of course, here, if I have a constant or omega or infinity, then I have f is big omega of g. This would mean f is big omega of g. So this theorem or this test is also repeated in the book, and you can see plenty of examples in there. I also want to go through a couple other tools that we can use to evaluate these limits, and then I'll work a couple examples in the next video. So real quick, before I work some examples, there's a couple tricks that'll be helpful with this. So the first trick is Lhopitals Rule. So this is one of these classic Calc 1 tricks for evaluating limits, and it's a really handy one for the limit test, specifically because we have these ratios. So this is Lhopitals Rule. All right, so in Lhopitals Rule, what do I have? Suppose I have a limit, and I'm trying to evaluate a limit of two functions, limit of f of n divided by g of n. So suppose this limit looks like, right, if I evaluated either the limit of f of n or the limit of g of n, if I evaluated either of those in isolation, suppose this looks like 0 divided by 0 or infinity divided by infinity, right? Then I get the following, and I'm going to write that down in a second, but suppose I have the right form for Lhopitals rule to work, then what I can do is to evaluate this limit is I can say this is just exactly equal to the limit as n approaches infinity of the derivative of f divided by the derivative of g. So derivative of f with respect to n divided by the derivative of g. And my note is that this only works if the original limit looks like 0 divided by 0 or infinity divided by infinity. And I'm being a little bit informal with this, but for our purposes, this will be fine. So it only works if original limit looks like 0 over 0 or infinity over infinity. Limit looks like 0 over 0 or infinity over infinity. Okay. And so, we're literally in the limit test, we're literally computing, limits as n approaches infinity of these ratios of functions. The limits are almost always, like our form in algorithms will almost always be infinity over infinity. So Lhopitals rule will almost always work for these purposes. Okay. So there's another one is called Stirling's formula or Stirling's approximation. This one will be handy when we're thinking about factorials. So Stirling's approximation is the following. And this is going to be, again, a little bit informal, but for our purposes in evaluating limit tests and things like that, this will work just fine. What this says is that as n factorial, which is, it's a difficult kind of expression to work with because it has this product of a whole bunch of different n's in it. What this says is that n factorial, when n approaches infinity, starts looking like the following expression. Right? It starts looking like 2 pi n, right, times n over e to the nth power. Right? So there's a relationship between n factorial and this n to the n divided by e to the n times the square root of n times the square root of 2 pi. That ends up, these two get closer and closer and closer the larger n gets. And so this is a handy little approximation. Some call it a formula, but it's not really a formula. Handy little approximation to use when you're evaluating these limit tests for functions.